Well, there's a book, Scientific American. It talks about what the comb is. I'll just try to speed up here if I can get my advancer to be working. So let's then take this picture that we have the optical comb, and it was really a great kind of thing. And then I'm kind of coming towards the time for retirement. I need to go take Lindy camping, and we need to work on our mountain place. And so these things are a little bit becoming relatively small compared with the contributions and new ideas that are brought in by my replacement guy, Dr. Jun Yi. And I'm pretty sure that you will hear about him in some kind of official way. And he's introduced a few things that I'm hugely proud about, and I'd like to tell you a couple of these. So one of the things is how to make a laser stable. You lock the laser so the wavelength fits between these mirrors. There's a mirror on the top and a mirror on the bottom. This shape is one that those of you that are inclined mechanically will recognize as an attempt to try to make it have strong strength in the middle and not much mass at the top. So if you hold it in the middle, this is some kind of an anti-vibration design. And in itself, that's a breakthrough. If you want to pay your $20,000, you can get a cavity like this now and have a laser that's 1 hertz on your tabletop. No person on the earth could do that 5 years ago. So it's progress. And if we have something like that in Jilla, we can send that signal by fiber over to our pals in National Bureau of Standards, now NIST. They believe in horizontal cavities. Anyway, when you compare these by using the comb as the frequency displacer, you end up being able to show that probably both labs have lasers that are 1 hertz wide. Now, who cares about 1 hertz? Well, of course, national labs are going to care about that. And of course, people that try to build an accelerator in Switzerland or in any other place, they need to get it all synchronized. And so this way of transmitting the comb information to get the synchronizing information at the different places where the accelerator power supplies are, that's a breakthrough. And here's something which is going to be very interesting for us. I'll come back to what we can expect from these guys. This is a telescope that's being built in Chile. It's an international collaboration. These are huge telescopes, and their intention is to catch millimeter waves, even sub-millimeter waves. And that's really important because that radiation can come to us from near the time of the Big Bang, and we can see it. If we pick light, there's dust in the way, and we don't get to see the light. So now these are most meaningful if you can record the electric field, and so you need a reference wave. And so I've got just the step right up. I don't have a way to sell these, but you can make it yourself. This community was very quick to pick up on us. If you want to transmit frequencies, you can have 17 digits at 1 second. You can transmit a millihertz out of the 10 to the 15 hertz. It's just totally impressive. Now, what you will have contact with, I guess maybe in 5 years, is now when you have an annual physical exam, that you go in, they take some blood, and they put it on a glass, and there might be 1,000 little patches where there's proteins and antigens and stuff. And depending on what your doctor has ordered, they analyze this, these few little millimeter squares, and give you what the result is for your hemoglobin or whatsoever. This is something which works on air. I'll show you that in a second. But suppose you had this pulse laser, femtosecond pulse laser. It comes in and you fix these mirrors so that the bounce around time just matches the interpulse time. So that's a comb built up inside. Now if a molecule goes inside, the light goes back and forth maybe 100,000 times, and so there's a good chance that a molecule will make some absorption. Well, each molecule has its own absorption band, so if we take this light and spread it out so that its wavelength spread out, well, you can see that the color is changing, and so you know the wavelength is different. What you don't see in this illustration is this is actually composed of 300,000 separate colors with big dark gaps in between. This is a comb that's been made by nonlinear optics. And here's the absorption of one kind of molecule, the absorption of another kind of molecule. And there are so many test points on any one molecule that we could separate it, even if they were overlapped. so this starts to be an interesting way. Now we have the possibility to have one of the overworked students looking a little green from having been in the lab for all those nights, and he can put his breath into this cell. The light goes through, it's spread out into a spectrum, and this is just like you have in the camera, except that this can pick up infrared wavelengths, where these molecules are the most sensitive. We can get a spectrum out of that, and this spectrum for one particular case can look like this. So let's look at the bottom. It goes from 1.6 something to 1.6 another something. And if you magnify this zone, then you can find a spectra like this, and it's got water in it. Of course, that's totally natural. It's got methane in it. Well, I didn't know that I was making methane in the breathing, but okay, that's fine. And what's interesting is this panel. These are all carbon dioxide, CO2 absorption bands. The blue is the human breath. And these strokes down at the bottom have their amplitude, their size, and their position out of some tables that NASA has made for atmospheric. So some molecules are made out of like carbon 12, oxygen 16, but some others are made out of carbon 13. Well, there's 200 regular carbons for each carbon 13. But what you see is that these isotope lines are about the same intensity, whereas the source lines coming into us, carbon in the environment, is 200 to 1 split, and these other isotopes are also split. So somehow the body is working as an isotope-sensitive filtering machine. And I kind of wonder if the body realizes that these molecules that have the wrong isotopes are not for them. It's kept the carbon and sent out the carbon-13. Who knows? We try to get some support for this. You need to find a topic which is interesting. Here was one proposal where technically it's a superb proposal. It's collaboration with a high-level guy on lung diseases and with our group on spectroscopy. But the physicists say, well, I'm not sure that this is an important job, but it looks like your optics would work. And the medical people say, this is an absolutely important job, but no one has ever done an experiment this way, and so how do I know that your apparatus will work? And how can I tell them, dude, this is the first time it's ever been done. How can you be so stupid? We're trying to tell you that this would be a big thing. Trust us. And so here is where the United States is in a challenge now, because we insist on success. We tackle smaller problems so that we never fail as a manager. And what I just love about coming here is to have people from a company, and they say, well, it would be really good if we had a university here, so we'll get this together and we'll start and we'll believe. And Honeywell, with this initiative, puts me here to help some of you think that, oh, it would really be fun to be a scientist. I'd like to do that. So I hope you do make that decision. It's really a good life. So this multispectral diagnostics, for example, it's good screening for diabetes. The only thing which is the problem with this system is that I don't know how you monetize it, because you just use this one apparatus. It costs around $50,000. The doctor can buy it himself, have it in this place. Each person comes in, blows in this. Computer works for 2 minutes, gives you the spectrum. The doctor says, wow, you've got a lot of ethane. And he knows that that's connected with cancers where omega-3 is involved. And omega-6 lipids are connected with pentane in the human breath. That's facts, but we don't know what it's for yet. Let me talk about the high precision stuff, because this is what's exciting to me. We put the standard, the best standard that we have is the cesium standard. People have been working on that for 60 years, and during that time they've improved it by a factor million. That's improving it 10 times by each 10 years. It now has 16 digits, but one is really more or less against the rock wall. And so it would be great to have some new kind of technology, such as our optically based clocks. And in 2008, 3 clock systems were shown to have an accuracy potential more than the cesium by some significant factors. So it's more accurate than any standard that we ever had before, but accurate isn't the right word, because to be accurate it has to be traceable to the standard, and so the standard is fuzzy, and so we can never do better than that. But we can compare these ones to themselves. There's atoms or ions like this, mercury and so on, and atoms, we've got good technologies for holding them steady. And so you get to the place that we can have all these different kinds of atomic clocks, and now for the first time, the little boy at the front is going to come up and say, "Mister, you've got all these different kind of clocks, so they keep time at the same rate." Well, that's an interesting question. I'm really glad you asked, because what that is called cosmology. This is really getting down into the guts of how nature works. All the atoms the same? Oh, all the atoms the same here, but it used to be we would compare our stuff with Chinese people to see, since their Chinese isotope abundances were different, they were made by a different process. So I come nearly to the end if I can show this comparison. In the NIST, they had a clock that was based on mercury and another clock that was based on aluminum. And they measure for a year up to year 2000. And here's the frequency ratio going along. And perhaps the safe bet is that you would say, well, okay, there's a lot of uncertainty in these measurements, so I'll say that there's no change. That's certainly the government employee position. But what do you think? Maybe it would like that tilted line. Oh, and by the way, this is 2007. We're in 2011. I just got to get these guys to put some more data points onto this curve. If you take the information out of this frequency range, you can make measurements between different clocks. So this is the purple is one color, and here's optical clocks against, and here's another against each other. And finally, on this axis is something which I like. It's called the fine structure constant. It's a number that physicists love because they don't understand what in the world it is, where did it come from. It effectively measures that magnetism is weaker than electric interactions. The factor that it's smaller is 137.03599992. And we know it to plus minus 1 or 2 in this very last place, 8 or 9 digits. And we don't know whether that number should be 137 or 14 or 2 or 1. We have no clue about it. And so that brings up the issue, which I would come to on this next topic then. Does this change in time? Well, let's take some particular length of time. It changed less than 1 part in 3 million over that length of time, which was the age of the universe. So in our universe, if you're doing kind of undergraduate crude work, like at parts per million, then you'd say, okay, alpha is a constant. Now, in the Physical Review of this week, Physical Review letters, you'll find papers from a group in Australia. And they say if you look this way at old stars and this way at old stars, this alpha that controls the splitting of some lines that they can resolve is different, they say. And I don't know, maybe it's true, who knows. The last thing which I would like to say is that if you look on these Hubble deep absorption plates, there's so many stars, galaxies. The density in this is only 500 million years. It's just 5% of the age of the universe. It's just huge matter densities. And the thing about them is that they seem to have unusual dynamics, which we even see in our own galaxy, that it can spin faster and not blow apart than you would thought. So we introduced the idea of dark matter. It doesn't shine, but it holds it together. And so a lot of it has to be that. But then we find out that if you go even farther back in time, that there's something called dark energy that makes this explode. Well, these are just placeholders for understanding. But nevertheless, 75% of the energy of the universe is in dark energy, a pressure kind of form. That means we only have 20% left for dark matter, and for the stuff that we know anything about, that's like you and me and stars and products in metal from Honeywell or whatever, there's only 5% of that. So I can't imagine a more interesting time for my parents to have chosen to put me on this planet. Just fantastic stuff. So here's what our proposal is. Satellite experiment, and what these are, this is a Michelson-Morley system, once in 90 degrees in this direction, horizontal, and once at 45 degrees. So 2 Michelson-Morley interferometers. Here's the cell for an absorption system, and here's the light beams bouncing around in a prototype. So this was coming along very nicely until the previous president of the United States said that we're not going to do basic science anymore. So we're having a bit of a problem. Later on in the evening, after we've had some cerveza or something, we could have a discussion about how do we really reconcile the role of education, science, stuff that comes out of science, and is it more valuable to do this thing or another thing? It's not just denoted in money, it's what does it do for erasing dengue fever in Africa or some other kind of coordinates. So I conclude then with a presentation of my research group. It's got a few generations represented. This is about as big as we've ever been. What Lindy and I are involved in now is going into the schools. Here's a great group of kids asking questions and wondering. And what we find is that the youngsters, this is now in elementary school, they are just thrilled by having a little plastic tube that the marble can go down. It can go this way or go another way, and how does it go? They have never touched something like that before. Can you believe that? And here's another one. These girls are absolutely fascinated by turning these gears. They're interlocking gears on this whole board. And you could look at it and you know in an instant, okay, I turn this one, this is going to be counter-rotating, this is going to be rotating the same. They're just on there for 5 minutes looking at this, trying to figure it out. So I think we're touching somebody. So that's the story. Books and references are important. Here's a fantastic bookstore. Probably there's equivalent things for the young people that you have as nephews or nieces or so. And I thank you for listening to this a little bit extended talk. If you want references about my stuff, it's in here. The talk that I gave for the Nobel occasion is here. Here's another papers by my colleague Jun Yi. There's things from Lindy's group and from the NIST group. And finally, as I mentioned, we're in now the 51st year of the laser. So there's a lot of stuff on this website. So that's my story. I hope you have something to think about when you go on walks or talk with your colleagues. Thank you very much.